In this chapter, chapter 15, we've been studying non-renewable energy sources. We've learned about oil, natural gas, and coal. We're finishing up the chapter with nuclear energy. Nuclear energy in a conventional nuclear power plant is run by a controlled nuclear fission chain reaction. We'll talk more about that in a minute. That chain reaction that releases heats water, that produces high pressure steam. That steam turns a turbine, and that turbine creates electricity that's sent to our homes and businesses. This is a diagram of the fission reaction. We have an example of uranium-235, an unstable radioactive isotope here that is bombarded by a neutron, which causes this uranium-235 to split and release energy. And when it splits and releases energy, it also releases more neutrons that can go on and attack other uranium-235s and cause them to split and release energy. And this is a reaction that will keep going and going and going, compounding and get bigger and bigger and bigger as time goes on and more neutrons are released. And that will release huge amounts of energy as the reaction continues. In a nuclear reactor, there are control rods. And what these control rods do is they control the radioactive decay of the uranium-235. They absorb neutrons so that ever-increasing exponential amounts of neutrons aren't created, and this fission reaction doesn't run out of control. So it keeps the rate of reaction at a certain level so it doesn't get exponentially greater and release so much energy that there is a nuclear meltdown. This illustration shows the basics of a nuclear power plant. We have the uranium that is put into the reactor, and we have the control rods here inside the reactor. The fission process produces heat, and that heat heats up water in the heat exchanger system that produces steam, that turns a turbine, that turns a generator, and creates useful energy, about 25 to 30% efficiency, and that produces electrical power. In our water unit, when we study water pollution, we'll learn about thermal pollution, and nuclear reactors are one source of thermal water pollution. They take in water from some sort of external source, a river or a pond or a lake, and they use that water to cool down elements. And then it's returned into the ecosystem up to 10 degrees hotter, which reduces the amount of oxygen in the water and also is a shock to living things in the water just running into that 10-degree change. Radioactivity. Radioactive decay of uranium-235 or plutonium continues until the original isotope is changed into a stable isotope. The radioactive elements are unstable, having a different number of neutrons than the normal element does. So they change into the stable form of the element until it's no longer radioactive. Radioactivity are the nuclear changes, the changes in the nucleus of the atom, in which these isotopes, these unstable isotopes, emit particles, high energy particles and energy. That high energy is why they're dangerous to human beings. That high energy wavelength can cause damage to our DNA. Radioactivity types. What's emitted from radioactive decay? Alpha particles. Alpha particles are made of 2 protons and 2 neutrons. So these are positively charged radioactive decays. Beta particles are negatively charged. Gamma rays have no mass or charge but are a form of electromagnetic radiation. Sources of natural radiation include the soil, rocks, air, water, and cosmic rays. We are exposed to small amounts of radioactive decay all the time from these natural sources. And here are some sources of natural radiation and unnatural, well, being exposed to, like living near a power plant. About all sources on average were exposed to about 3.6 millisieverts per year. A sievert is a unit used to measure doses of radiation and its effects on biological systems. And you can look here at the different sources of radiation doses and the amount of radiation that you're exposed to. Half-life. You are going to need to calculate half-life, and it is likely that you'll need to calculate that on the AP exam. If you've taken chemistry, you've probably already calculated half-life. If not, we will go through this, and there will be some examples for you. It really isn't too difficult to calculate half-life. Half-life is the time needed for 1/2 of the nuclei in a radioactive substance to decay and to emit their radiation to become stable. Half-life is very useful. It can be used to determine how old rocks are, how old fossils are. So we use half-life to our advantage in these radioactive substances. Well, also carbon. The carbon-14 changes to carbon-12. We can use carbon to measure how old specifically fossils and bones are. Uranium-235 has a half-time or half-life of 710 million years. So this is very useful in measuring the age of very, very old things. Plutonium has a half-life of 24,360 years. And they also produce alpha and gamma particles. During operation, nuclear power plants produce radioactive wastes, including some that remain dangerous for tens of thousands of years. So not all of the hazardous radioactive material is used. It's still undergoing radioactive decay. Also, just breathing in the dust from some of these elements can be carcinogenic, very dangerous. Effects of radiation, we've talked about this a little bit already. Radiation can cause genetic damages. It can damage the DNA in cells. It can alter the genes. These genetic effects can be possibly not manifested in the person who receives the radiation, but can damage the egg and the sperm, and it becomes more apparent in the next generation. And it can cause somatic cell changes, those are the body cells, to tissues, burns. It can cause burns, miscarriages, and cancer. This is a diagram that shows the penetrating power of different types of radiation. You have the alpha particle, which stops at the human hand, the tissues. Beta particles, which are often X-rays, penetrate the human hand, and aluminum stops those. Gamma rays, which are emitted and can pass through thin lead, they're stopped by thicker lead. And then neutrons that move through concrete. Right, there is waste that we have to deal with when it comes to radioactivity. There's low-level and high-level radiation. Low-level radiation waste sources include nuclear power plants, hospitals, and universities. For a time, most of this radioactive waste was dumped into the ocean. Today, it is deposited into landfills. Then there is high-level radiation. This gives off high amounts of radiation. The fuel rods from nuclear power plants are a source of that. There's really no agreement about a safe method of storage of this type of radiation. What we have done and what we are considering doing with that high-level radioactive waste, bury it deep underground. Problems, it could be in the containers that it's sealed in, it could leak out. In the event of an earthquake, it could infect our groundwater. We could shoot it into space or into the sun. That's very expensive, and accidents could affect a large area. We could bury it under the Antarctic ice sheet. Well, the ice sheet, first of all, is disappearing, and we know that the stability of the ice is unpredictable. Most likely for the U.S., we are burying it into Yucca Mountain in the desert of Nevada at a cost of over $50 billion. It's 160 miles from Las Vegas, and it is transported across the country in trains and trucks, which in the event of an accident could be hazardous. Okay, a very controversial method of disposing of our radioactive waste is Yucca Mountain in Nevada. Deep tunnels are built into the mountain where the radioactive waste is disposed of, and large containers, large sealed containers. During the operation of a nuclear reactor, uranium does run out. And what you accumulate in the products, as the waste products accumulate, it inhibits the efficiency of the running of the nuclear reactor. So the fuel needs to be at least partly renewed every year. That waste does contain plutonium, which is radioactive in itself, and we could reuse that. We miss out on the opportunity to split that plutonium to make the operation more efficient. Plutonium and nuclear waste can be separated from those waste products, and clean plutonium can be used in a different type of nuclear reactor. Okay, advantages and disadvantages of nuclear power. The advantages: there's a large supply, there's a low environmental impact without any accidents. It emits about 1/6 the amount of carbon dioxide, that greenhouse gas, as coal does. There's moderate land disruption and water pollution, again without accidents. There's a low risk of accidents because of multiple safety systems, except in 36 poorly designed and run reactors in the former Soviet Union and Eastern Europe. The disadvantages are high cost, even with large subsidies, low net energy yield, high environmental impact with accidents. Catastrophic accidents can happen, like those at Chernobyl. We'll talk about that in a minute. No acceptable solution for long-term storage of radioactive wastes and decommissioning worn-out plants. And plants get old, you have to shut them down, and what do you do with that area that's radioactive? So that is a controversial topic too. It spreads knowledge and technology for building nuclear weapons is another disadvantage. The concerns about the safety, cost, and liability, having to pay for accidents, that is, have slowed the growth of the nuclear power industry, and accidents at Chernobyl and 3 Mile Island showed that a partial or complete meltdown is a possibility. You can see here that over time, nuclear power plants, their service is starting to decline. Most popular in the late 70s and early 80s, in the 90s starting to shut down, and the desire for them declining. Okay, some history of nuclear power accidents. First, 3 Mile Island, March 29, 1979. A reactor near Harrisburg, Pennsylvania lost coolant water because of mechanical and human errors and suffered a partial meltdown. 50,000 people were evacuated and another 50,000 fled the area. Unknown amounts of radioactive material were released. Partial cleanup and damages cost about $1.2 billion. Released radiation increased cancer rates in that area. And here's an image of 3 Mile Island. Another nuclear reactor disaster was at Chernobyl. In April 26, 1986, a reactor explosion in the Ukraine flung radioactive debris into the atmosphere. There were 3,576 deaths. Greenpeace actually estimates 32,000 deaths. About 400,000 people were forced to leave their homes. 160,000 square